Vielen Dank, Thomas Brandstätter, für diesen Überblick und diese Überleitung. Denn nun ist es an der Zeit, um abzuheben. Hinaus ins Weltall für die diesjährige Keynote. Yeah, it's time for this year's keynote. And when we think about IT security, we often and normally focus on our networks, our companies, our critical infrastructure here on Earth. But security challenges do not stop here on Earth. They do not stop here on our planet. They extend into space. And our keynote speaker today works at the European Space Agency and will share insights. Insights into how space missions are evolving, what kind of security challenges arise, and where research is most urgently needed. So please welcome Antonis Atlasis with his keynote, Security of Space Missions. Welcome.
Thank you. Good afternoon all. Just give me a few seconds to connect my laptop. To be on the safe side, to put also the power supply, of course. So good afternoon. My name is Antonis Atlasis. I work for the European Space Agency. I'm the head of the System Security Section at the Directorate of Technology, Engineering and Quality. Thank you very much for the invitation, and it's really an honor for me to be here with you today. And I'm glad to see events like this one where community gathers together in order to discuss challenges and define together the way forward on security aspects. I will start with a very small introduction about who we are. I'm sure that many of you know, but some of you may not have the full picture. So I will be very brief on this topic before I go to the main topic of the talk of today, which is security in space. So the European Space Agency is in principle the gateway of Europe to space. It consists of several member states plus many cooperative states. We have more than 6,000 workforce, and this continuously grows and changes. Of course, our objective is to explore and use space for exclusively peaceful purposes. This is also part of the ESA Convention. Where ESA is located, there are various establishments across Europe. The headquarters is in Paris, but there are several sites, as I mentioned, in Europe, also in the French Guiana, which is the spaceport. And there is quite some substantial funding, I would say, for space missions. But what are the types of space missions? We can categorize them in these 5 categories you can see on the slide. We can certainly say that many of them constitute part of the critical infrastructure. So because of this, you also understand the importance to be secured, starting from right to left to talk about navigation. I'm sure you all have heard about Galileo. Many people, when they hear about navigation, they think of GPS because it was the first system that offered navigation services. But Europe has its own system, Galileo, which is really important, especially in an era where you may not be able to rely on other systems. Also telecommunication systems, which continuously evolve from more old-fashioned traditional ones to more modern ones. We will come to this a bit later as well. Earth observation regarding topics like, for instance, to wildfires watching or flooding or even about weather, but also going sometimes even one step further. Human robotics exploration, going to the moon, to Mars and beyond, and eventually several scientific missions. Certainly not all the missions have the same importance in terms of security. You can understand that the ones that really constitute part of the critical infrastructure also have higher security requirements than, for instance, scientific one, but certainly security cannot be neglected eventually in any of them. I mentioned a bit that there are several sites where ESA is located across Europe. Where I come from, where I work, is the European Space Research and Technology Center called ESTEC, which is in the Netherlands, in Noordwijk. This is, I would say, the heart of technology and research for ESA, and it is also the largest establishment of ESA in general. And our focus is, as the name implies, is the engineering part. We provide support as tech as our directorate to more or less all ESA missions transversally, but also to develop technologies needed for future missions. There are a big number of laboratories, of experts, etc. Each one of them specialized to a very specific areas because it requires really top experts on every single topic, I would say, domain in order to materialize space missions. But this is about ESA, just a very small introduction. Let's go now to cybersecurity for space, or cybersecurity at space, which is the main topic of the talk of today. In order all of us to be on the same page, I will start with some very brief high-level introduction of the space systems, how they work, in order to understand also the threats on this. So this is what you can see here in this graph as it is now. It is the very bare minimum space system. You have the ground segment, you have a satellite, which constitutes the space segment, and of course you have the communication link with telemetry and telecommand. If someone wants to attack this kind of system, the attack surface in general is quite limited. You need to attack either the ground segment, through the ground segment to go to the space segment, or you need to somehow to try to attack the communication link itself. Usually it is RF link, so RF, of course, it is transmitted everywhere, more or less. So it is not impossible someone to try, but of course, this is why you need to have some preventive measures. To elaborate it a bit, we can add also the user segment. So satellites also offer services to users. This can be any kind of users, from telecom to navigation, etc., etc. It can be unidirectional or bidirectional, depending on the nature, can be a threat or not. But what has changed is drastically, I would say, the last years, is introduction of constellations with some ISLs either satellite links among the satellites for transmitting information, and eventually to connecting through the gateways and through the gateways back to terrestrial systems. So you can see that from the initial picture where it was just a ground segment and a satellite, how gradually evolve on a system where the attack surface really increases, which means also, of course, the challenges of security also increase. There can also be different approaches how you manage your constellation, how you manage what you call the platform, which is the main part of the spacecraft, plus the payload, which is the one that offers the services for which its spacecraft is manufactured, is built. So there can be some direct communication to the payload always through the platform. So everything is managed through the payload, through the platform, which means that, of course, the payload needs to trust the platform and vice versa. Or you can have different ways to manage it. You can have management of the platform itself, plus a management of the payload through independent telecommand of telemetry links. Again, as you can understand, these two approaches can also have different security requirements, which are a bit straightforward. In the one, you need to trust your platform since everything goes through it, also to the payload. In the other situation, it's a bit independent. If you want to have a look at the space architecture, this can provide some kind of an overview. I know it seems a bit complicated, but you can identify the main points there. I'm focusing to the space segment, not because the ground segment is not important, just to be very clear, but in general, the ground segment to a great extent resembles a lot an IT system. So all the security challenges or the security solutions that you encounter on IT systems, you can also use them, or you will find them in a ground segment again to a great extent. What is really different, what is really unique, I would say, is the space system itself. Another thing I would like to point out is that all this information is public, meaning that people can understand, can see the standards, can even analyze them. I'm mentioning this why? Because I have seen many times in the literature, for instance, when research is being done, referring to space something like a security by obscurity approach. I believe this is not true. When you have something which is published as a standard, it cannot be security by obscurity because everyone can take and download it. And I will also explain this a bit later. Going back to the architecture here, I will not going to analyze, of course, all of it. You can see the platform on the left and payload on the right and how do they connect. From a security point of view, there are two units here that are the main components, typically not the only one, but certainly the bare minimum in order to secure your satellite. It says security. It is a generic term used in principle for, I would say, units that offer authentication or authenticated encryption for the telecommands and the telemetry. Telecommands are the commands that allows the ground station to control a satellite. What telemetry is the data you receive from satellite. For instance, can be health status data or logs or whatever. So you can see that based on this architecture, there must be at least two security units, one for the platform on the left and one on the payload, and everything in terms of telecommand telemetry has to pass through there in order to be authenticated and decrypted or only authenticated. Just a very high-level architecture in order to get you up to speed about how a satellite may work. Of course, you have the processor, you have an onboard computer, you have a payload processor as well, time reference, etc., etc. Yeah, but these are the basic, I would say, elements that are relevant for the security point of view. Now, on the real world, when I say real world, I usually refer to the terrestrial world, to the IT world. We use MITRE ATT&CK a lot for the tactics, techniques, and procedures of APTs, of adversaries in general. And MITRE ATT&CK, as you know, I'm sure that since you are part of the cybersecurity community, is a collection of TTPs based on cyber threat intelligence from real attacks on the internet. Of course, on space, we do not reinvent the wheel. We take the lessons from the internet and, of course, we tailor them, we adjust them to the specificities of space. So MITRE ATT&CK was a perfect example how someone can categorize the TTPs, tactics, techniques, and procedures of various attacks, but some different approaches, adjustments were needed. For the ground segment, again, to a great extent, because as I said, it resembles a lot an IT system, MITRE ATT&CK can be applied as any other enterprise system. But the space segment is really, really unique. And this is why we have created a MITRE ATT&CK-like framework or knowledge base, which is called Space Shield, where you can see it follows exactly the same philosophy. It has exactly the same tactics, as you can see. Apparently, the techniques and the sub-techniques can differ. If you go to the link, you can browse through it and see the various techniques or sub-techniques, etc. By no means this is something complete. It started internally, especially because we wanted for us, in order to elaborate on the potential security threats against our systems. So it is far from being perfect, and there is always room for improvement. But it is something that allows us to, I would say, identify what are the potential key points also for research. One main difference in comparison with the MITRE ATT&CK is that, as I said, and as you know, MITRE ATT&CK was compiled based on the cyber threat intelligence gathered through the internet, through the various attacks. We don't have the same information in space for many reasons. Also because the attacks are more limited, or if there are some, maybe they are not shared much. So in principle, this framework, this knowledge base was constructed by using our mindset from attacker's point of view to think what can go wrong, and then after identifying what can go wrong, to try to find out how we can mitigate, of course, these threats, because eventually this is our objective. It is not the only effort of such a a knowledge base. There are also frameworks like this from US. One very famous one is called Sparta. But all in all are, I would say, along on the same lines, meaning that they follow the same philosophy. Now I would like to give you an overview of the protocol stack. You all know about the TCP/IP stack that we use on the internet. Space has its own protocol stack. It has some similarities, but it also has many differences. Why is that? Because, again, Space has specificities, especially in the past, even more regarding bandwidth, regarding processing power, etc., etc. So, first of all, I'm sure that you all know about ITF, which is the Internet Engineering Task Force that standardizes the RFCs, the standards protocols for the Internet. So there is something similar for space. It is called CCSDS. You can see the logo on the top left. So CCSDS is a standardization body for space. And it is an interagency standardization body where agencies like NASA, like ESA, and many European ones like CNES for France, or DLR from Germany, or the UK Space Agency, etc., or JAXA from Japan, etc., participate there in order to agree and specify the standards, especially the protocol standards for space, in order also to ensure interoperability, because eventually, like in the internet world, interoperability is key also for space. You can see the stack. Of course, you see that the protocols are very different from what you know from the internet. But also there are some similarities, like the IP you can see there. So how this stack is secured? If you recall the initial graph that I presented to you about the ground segment and the satellite, you realize that it is mainly, or it used to be mainly, a point-to-point. So when you have a point-to-point connection, it makes sense to protect your information at a link layer. This is why the first and foremost security in a protocol level is offered through the protocol called SDLS, which is applied on the data link layer of the OSI stack, which protects all the protocols of layer 2 that you can see there at the bottom. I will talk a bit more about SDLS later. But it's not the only one, of course. We have IP. It is used in some cases, and probably it's going to be used more and more, especially now that we have the convergence between space and terrestrial networks. IP, it is used in a bit of a different way because it is encapsulated in a specific protocol and then encapsulation packet. So it is not over Ethernet directly as it is usually in the terrestrial networks. And at the application layer, you typically have the bundle protocol, which is for the so-called delay-tolerant networking. Delay-tolerant networking or disruptive tolerant networking are the networks where you can have long delays or the connections are not permanent. So you need a different way of communicating there. Imagine to have some mission, like, say, to Mars and beyond. You don't have communication all the time, and not only that, you don't, the packets to arrive take some time from 10 minutes or even more, depending on the distance of the planet. So you cannot rely on typical, for instance, TCP/IP structure, but rather in something more flexible. In order to secure this, there is equivalent BPSec, the bundle protocol security, which nevertheless is also an ITF standard. So you can see the bottom line is that you can see there is still a protocol stack here, but it's different than the one on the internet. And each one of the layers, mainly the layer 2, the layer 3, and the application layer, have their own security protocols. The vast majority of the missions rely on SDLS because, again, because of the nature of the connections, which is link layer based, it makes more sense to protect the link layer itself, at least in the vast majority of them. Let's start discussing a bit now, starting from the physical layer. And someone may wonder that, okay, it's not that easy to capture some information from space because you may need big antennas, etc., which to some extent is true, but it doesn't mean that it is impossible. And as an example, I will present you something which does not come from ESA, does not come from us. You can find it easily on the internet. It is a radio amateur. I don't think this person is an amateur, to be honest with you, that captures signals from space, and he manages to decode them and to analyze them and even to reconstruct images, etc. I'm giving just some examples here. He's doing a great work, but the message here is not about the specific work. The message is that getting the images or getting the signals from space and capturing and analyzing is not something extraordinarily difficult, which means that you cannot rely on this, of course, in order to ensure that your signal to be protected. You need to rely on typical security mechanisms. So if you cannot rely on the physical layer itself, what can you do? I mentioned before the SDLS. I will explain you a bit about the philosophy of SDLS without diving into the details. SDLS is very simple. It resembles a bit from IPsec suite, the ESP protocol. At the top here, you have a frame. Remember, this works on layer 2. You have a frame, let's say a TC frame, telecommand, which is, of course, initially unencrypted and unprotected. You remember there is this security unit in the architecture of the satellite. Then you take the frame data and you put a security header at the trailer. And then you have, of course, the space link protocol frame header in front and the trailer of the frame itself following the whole frame. You can see some of them are optional for some good reasons. And I have analysis underneath about the security header. With this approach, you can have either authentication only, for instance, by adding a MAC, for instance, in the end, a message authentication code, using techniques like HMAC with some hashes, as an example, or CMAC or GMAC. The same algorithms and the techniques that are used on the internet as well. And the security header defines, for instance, the SPI and the initialization vector if you have some IS implementation, etc. So all in all, you can encrypt your data, your frame data, and you can authenticate all your headers as well. This is how frames are protected on space. And again, you can see on the top left and top right two blue cover pages. These are the cover pages of the corresponding standards. They are called the blue books from CCSDS. When the terminology is that the blue books are the ones which are the standards on the CCSDS, I would say, arsenal of books of standards. Unfortunately, I only scratch the surface on each one of these topics because I want to give you a generic overview of many security aspects from space. So this was about the protocol. You may wonder, what about the crypto part? Again, as I said before, we do not need to reinvent the wheel. So we will not, and we do not design our own algorithms. It would be stupid for many reasons. We just adopt what works and we see if it can fit in our needs, and if it does, we use it. So the well-established standard for symmetric crypto, for instance, for more than 20 years now, actually, is the advanced encryption standard. So the same one is actually the main one used also in space. We even are a bit, I would say, more strict than the outside world, where we do impose 256 bits key and the 128 only for compatibility purposes with old missions. Several, or mainly two modes are supported, the counter mode and the Galois counter mode. The one is only if someone, for whatever reason, uses IS only for encryption and has authentication by, for instance, HMAC. And the Galois counter mode when you want to have authenticated encryption using IS only, which is typically more efficient. However, things are changing, and this is what I'm going to mention a bit later. And things are changing also for the crypto part, and the space world cannot be unaffected by this change. But probably I will park this observation for a bit later. I mentioned SDLS, which is the main protocol that offers security in space communication links, I mean, which is on layer 2, but it's not the only one. Just a very quick glance that I mentioned before about IPsec in space. So there is a standard about this, IP over CCSDS and the network layer security adaptation profile, which is more or less a profile of the typical IPsec we have on the ground for space. And on the right side, on the red one, is the bundle protocol security for the application layer, again, for a very specific use cases. So this is the story so far. So the bottom line is the following, if we want to summarize. Traditionally, space missions were quite simple. Ground, communication link, space segment. Usually your payload was more or less of the same stakeholder, so the owner of the mission was also the user of the payload. So you had a relatively minimum attack surface, and you can secure the communication link, of course, using protocols like SDRS and well-established crypto mechanisms. Let's now go and see what is changing. In reality, many things change, and I'm sure that you are also experiencing these changes. First and foremost, we have entered the so-called new space era, where new space means many things. It means that we go fast, we take more risks. I'm not talking about this, and I'm talking in general about the space community. We take more risks, we rely mostly on codes, commercial off-the-shelf products. And why is that? In order to minimize costs and in order to accelerate developments and deployments. Which all of these approaches, of course, make sense. And on top of all of this, we have more and more and more launches. You know about, of course, Starlink, but it's not the only case of the many satellites that are being deployed. But all these advantages, because I believe we all agree that, yes, we need to go faster, yes, it would be good if we can go cheaper, yes, it would be good to have even more satellites. All this comes with a price. There is nothing that comes for free. And what are the prices in this case? Let's take the pictures again from left to right. Commercial of the shelf. This means that you bring potential vulnerabilities from ground to space. Someone can say, okay, but anyway, even if you don't have a codes that you adopt from terrestrial networks, it doesn't mean that you don't have a vulnerability in bespoke applications. That is for sure the case. I mean that at the end of the day, vulnerability does not depend if it is codes or if it is bespoke. You can have it either way if you don't pay attention how you develop your products. The only difference is that then it becomes even more easy for someone to first to maybe know about the vulnerabilities, these ones, and secondly, to try to potentially exploit them. Secondly, we have also the threat of the supply chain attacks. I'm sure that you have heard about cases like the SolarWind several years ago, or even the Log4j that happened, I don't recall exactly, 4 or 5 years ago. Log4j vulnerability, a small one, in Apache, which is open source, but this software was used even by commercial products, so eventually many important products were found to be vulnerable to it. The important thing here is that at some point, people found out that this software, the software, no vulnerability, was also present in, for instance, on the rover that NASA uses on Mars, because they were using also Apache. So this is one way how you can potentially bring vulnerability through supply chain to space. Now, just to be very clear, NASA stated very clearly that this does not affect us, and they take, of course, cybersecurity very seriously. I have put the quote here from NASA website. And even if it was present, it doesn't mean it is a piece of cake, someone to talk to their rover on Mars. But it is a very good example that shows the more that you rely on codes, for instance, the more that can be the case that implicitly or not to inherit vulnerabilities and bring them through supply chain also to space. And the problem is, while on the ground, you can go through some patching process relatively quickly, hopefully. On space, you can still go through patching process, but it is certainly more challenging and more difficult to implement. So you need to be, in first place, more robust in order to be able to mitigate even cases for one reason or another. You cannot deploy a patch quickly because you may risk of losing your spacecraft. And so it's better to have some other measures in place in order to mitigate this, such cases. But we also have new technologies that are entering the arena, I would say. You all know about SDR, software-defined radios. Great, we're all happy about it, and more space missions will rely on it, but the more flexibility you have, the more you need to be sure that it will be secured, not to be abused. Very simple. I will not refer a lot to the AI. It is not a space-unique topic anyway, but I will mention a bit the quantum threat. To to cryptography. I'm sure that you have heard about it, about the quantum computers. They are not materialized yet. It will take time. Some experts say from 10 years at a minimum, some they say to 30 years maybe. Some even doubt that eventually there will be quantum computers good enough in order to be able to break crypto. But the thing is that you cannot take the risk, or cannot live with the risk that some point these computers will materialize and will threaten the crypto. So there is a lot of effort already for years. NIST launched a competition in 2016 about post-quantum crypto. We have the first standards already published. Big companies on the internet have already migrated. Some browsers already support post-quantum crypto. So we also want to do the same in space, meaning that to have quantum-resistant solutions in space. For the internet in general, this transition takes time. And also you need to take into account for how long you need to protect your information. Because of this store now, decrypt later approach, which means that, okay, I don't have a computer now, quantum computer, but I store all the data. And if these data are valuable after 20 years, when I will have the quantum computer, I will decrypt them. So you need to take into account several parameters. This is a famous Moscow equation. But in space, on this topic at least, we were a bit lucky, allow me to say. Why was that? Because, as I mentioned before, it was mainly point-to-point links. And on point-to-point links, communication links, we used SDLS, as I mentioned. Since you have point-to-point with minimum number of links, you could rely on symmetric crypto. As I mentioned, we use mainly IS. And symmetric crypto has proven to be less vulnerable to quantum computers. There is a debate about the size of the keys, but in the worst case, let's say you double the size of the keys to 256 bits, and you are good to go. And this is why the standard that I mentioned before mentions the 256 bits key. In any case, because we change also in space in other aspects, like the mega constellations part, when you have 2 satellites, 4 satellites, 10 satellites, even 40 satellites, a constellation of 40 satellites, you can still manage it using symmetric crypto. But when your satellites, the number of satellites start becoming hundreds or even thousands, and you have the ISLs in the satellite links between the various spacecrafts, then it's the time that you introduce the asymmetric crypto. And when you introduce asymmetric crypto, it is the time where you use a quantum-resistant solution. So this is another key change that is going to happen to space in the years to come. What does this mean for space security in practice? I believe I also already mentioned some of this about the large mega constellations, need for asymmetric crypto while considering quantum threat to crypto. So we need the solutions you have for the internet again, like for instance the MLKM standard by NIST for key exchange to be used also in space. We may establish our own protocol, but not our own crypto again. And this protocol is currently under standardization through the CCSDS body that I mentioned before. It's a significant change, I would say, and we work already with both academia in first place because the protocol was designed for us by academia, and now with industry in order to implement it in future crypto. So this is one change for sure. Also, we may have even more the so-called federated missions. Imagine the case where you have, for instance, a constellation that it is used for Earth observation, and then you have a constellation that offers a, let's say, the backbone network, as you call it, on the internet world, right? So you want to use a backbone network in order to transfer your images that you collect through Earth observation satellites. This, in principle, is a federated constellation. Or you can have what I have here in the third row. There are missions which are being planned both by ESA and NASA around the moon, the so-called LunaNet, the network to the moon, where there are going to be different gateways from NASA, gateways from ESA, and to the moon to have rovers from NASA, establishment from ESA, or even other agencies. So there are many players there using the network of each other, because you cannot afford each one to have their own gateway. But in this case, it is where, again, you create some federated network, because you don't want one player to control, for instance, all the keys. I mentioned a bit about the DTN, delay-tolerant networking. When you have, for instance, if you go beyond the moon, then you start really experiencing the challenges of delayed packets or disruptive communications. And, okay, you have the protocol like the bundle protocol. The key management becomes challenging, especially if you don't want to stick on symmetric crypto only. And another part that is changing a lot is the commercialization, of course, and the need to optimize the missions in order to host various payloads. Meaning that in the past, as I mentioned, there was a mission with a specific objective. So the stakeholder of the whole mission was, or the mission owner was only one. Now we want optimization, we want commercialization. So there can be companies that they build a constellation that they want to offer services to others. These services can be to commercial other companies or can be even to governmental entities. So the question comes, when you are on the satellite, how do you trust each other? How do you trust, for instance, that the payload of the other commercial entity will not harm you? And the situation can become even more tricky when you have a combination on the same platform of commercial and governmental or semi-governmental payload. So all these are topics that introduce new security challenges also in space. And last but not least, to also have a great, I would say, spread of telecom networks also in space. You know it. We experience it. Starlink paved the way on this, but it's not only about Starlink, of course. Europe prepares its own constellation of this regard, the telecom constellation, with similar capabilities. And in this type of constellations, the time will come that we will see protocols from the ground to space. I give some examples here. There is already ongoing, for instance, on 5G, work ongoing on 3GPP group. 3GPP is the standardization body for 5G. Of course, this is well standardized and used on the ground for years, I would say, as an evolution of the previous generations of the mobile networks. But in the new releases, we see for first time use cases for the so-called NTN, non-terrestrial network. So with a bit of a digging on the 3GPP standards and releases, you will see that there are at least 3 different use cases for the bringing 5G into space, which means that we will have this interoperability between space and ground using 5G, which is, of course, great. But, of course, on the other hand, introduces security challenges. And there is a lot of discussion more and more about seeing protocols from the internet also in space. In the past, there was no discussion about it because the throughput was minimum, because there was no need, etc. But now we use bands with more bandwidth, bigger throughput, so this becomes possible. Also, when you have a LEO constellation, low Earth orbit with minimum latency, then it is feasible to have this kind of communication protocol. So we see that the two worlds are coming closer. There is a convergence, which is great for interoperability. But of course, this very limited attack surface that I showed at the beginning, this is going to change. I talk about the quantum threat to crypto, so I'm not going to elaborate on this further. Just for those of you that you may have not heard about the impact on the table on the right, you can see what the quantum computers will mainly affect. You can see, for instance, that everything based on asymmetric crypto like RSA or elliptic curves will be broken within hours, again, if and when quantum computers materialize. So, of course, no reason for panic, but on the other hand, you cannot take the risk and wait. And also talked a bit about the 5G. Now, on the 5G, there can be different cases. I mentioned that there are at least 3 defined so far in the 3GPP standard. These are listed here. The one and the most the most interesting one from the point of view that it provides the most flexibility probably, or one of the most flexibility, yeah, is to have a full GNOB on board. GNOB is in principle the 5G, let's say, access point that we have on 5G towers on the ground. Regenerative means that in order to implement, of course, this capability, you need your antennas, your payload, not just to retransmit something, as it is in the case of bent pipe payloads, but rather to really process, really decode the signal and then process a full stack implemented in GNOB. I have a graph about it later in the next slide. The other use case, identified 3GPP for NTN again, for non-terrestrial networks, in the store and forward, for delay tolerant services, not in the deep space, as I mentioned before, but around Earth. Imagine you have a satellite that goes around the Earth, and because you have just one or two satellites, you don't have permanent connection through some other space network, but the communication is really disruptive. So this is why it is delay tolerant, because you wait for the next pass of the satellite in order to get your package or whatever. And the final use case, which is this one is the most interesting, is the UE satellite to UE communication, the so-called direct-to-device also communication, where you can be on Earth and using a satellite to communicate with someone else directly on Earth. All these are extremely nice use cases, and when implemented, will be fantastic for the users, but each one of them introduces its own security challenges. Just to give you an idea, this is a very high-level security architecture overview of 5G. S would be implemented in an NTN network, a non-terrestrial network. I have put the stack. On the left, you have the user equipment. You have two planes, the user plane and the control plane. User plane is the one at the bottom, the blue one. The control plane is, control plane is a blue one. The user plane is a green one. And I have put some small satellites on top in order to understand easily what the difference would be depending on the implementation. 5G, it is true that 5G brings a lot of security improvements in comparison with the 4G and the previous generations, which is great. Just to give you maybe an example, the so-called SUPI, the information of the subscriber, now it is protected end-to-end from the user equipment to the home network using public cryptography. This is one of the biggest advantages, I would say, on security. Also, you can see that there is a specific layer over there called PDCP, which is the one that also offers security between the GNOB and the user equipment. The GNOB is the big rectangle, kind of rectangle in the middle of the graph, where the satellite, just underneath the satellites. So this is a GNOB, which is split in the so-called DU and CU. Apologies for terminology, but it is important to see how this is affected depending on the implementation. And you can see the PDCP there, which is, you can see the log, which is the one that secures the connection from the user equipment to the satellite, or at least to the CU. And from the CU to the core network, you have some other links which are protected based on the 3GPP standard, are meant to be through some kind of VPN, like IP-SECX, for instance. IP-SECX is a mandatory one, and DTLS is a kind of an optional. Now, depending on what you implement, why I'm saying all this? Just to show that depending on how you implement the deployment on NTN, the security changes. If, for instance, you have a transparent payload, which is the case on the very left, in principle, your satellite acts only like a mirror, which means that you don't open any kind of attack surface, but on the other hand, it can be used by anyone in order to use your satellite as a kind of a mirror to transmit their own data. You cannot hack, but you can exploit the bandwidth offered by this satellite, to put it like this. And you may have heard about some incidents that there were 2 or 3 years ago from TV, commercial TV, and some channels being hijacked and broadcasting propaganda for specific states. It was because these satellites indeed were using this bent pipe approach. Then you can have, I will go to the one on the right, the full genome be on board, where the full genome be supplemented on the satellite. In this case, you have end from the user to the satellite protection. Everything is protected and authenticated, since the log it is inside the satellite. And then from there, you protect using the IT-SECX channel. And you can have also something in between, which is the split tube, where in this case, the DU is on board and the CU is on ground, which means the CU, your channel between user terminal and the CU is protected still, but PTCP is on ground. So you have end-to-end protection from user terminal to space and to ground, right? But on the other hand, means that on its own cannot offer, for instance, authentication. You cannot authenticate on the satellite because PTCP is on ground. So it's on the other hand, the full genome board authenticates on the satellite, but you need to trust the satellite because it is decrypted there. This is why it needs to be considered as a trusted node. So you can see that each implementation has pros and cons from a security point of view. Which one you choose, depending on your objectives. What is your highest priority for your specific objectives? I'm just saying here that solutions are there. The way you implement may change the security perspective. I mentioned a bit before about the architecture of Savoir. One of the changes I mentioned is that you have the payload at the very end. One of the changes I mentioned is that we live in the era of commercialization and industrialization, which means that we want more and more satellites to offer more services to end users. This is why we have several payloads. You can see at the bottom, there is a bus, an onboard communication bus. There can be different standards, different protocols. There are different standards and protocols. The problem is that, typically speaking, for ages, as I mentioned before, we used to have missions with specific objectives and very specific mission owners. So sharing one bus between your payload and your platform was not a big deal. Now, from the moment that you start adding several payloads, and some of them can host third-party applications or can even be third-party payloads from the beginning, some of them with a potential supply chain issues, to put it in a generic way, automatically it becomes a matter of question mark whether you would trust to have them on the same bus or not. And all these protocols used on avionics buses were designed with the principle of robustness, of safety, but not necessarily with the principle of security, having these different customers, I would say, on one single satellite. Military standard 1553, which is used in aircraft like F-16, it's very robust, but it suffers from vulnerabilities which are known and published in the literature for many years now. CAN bus, also very well known, especially because it is used also by the car industry, also suffers with the same vulnerabilities. There are also some other protocols like SpaceWire, which is this ENISA standard, aiming to increase the throughput on the satellite, and some other a bit more robust on security point of view, like the Time Trigger Ethernet. I'm just trying to say here that because of these changes on the satellites, the problems that we didn't face in the past in these technologies, like the avionics buses, will also come into place. This is a bit of a summary of some kind of avionics buses and the problems that they may encounter. If you search, you will find a lot of work on the literature. There's a lot of work for military standard 1553, a lot of work for CAN bus. There are even solutions proposed, for instance, how to authenticate the CAN bus. From a scientific point of view, it is very interesting. From a practical point of view, sometimes cannot really work extremely well. Why is that? Because these protocols were meant to have extremely small size of packets, I would say. So if you had a few bytes, let's say 20 bytes, 20 bits of information through this avionics buses, adding, for instance, a 256 bits tag it's an extremely big overhead in comparison with the information that you want to transfer. This is why I'm saying that it is not really practical, no matter if there is a lot of work on this in the literature. Also, someone can say that, okay, I can find a smart solution to maybe to do something. The key management issue on the spacecraft still remains, where each one of your components that you want to authenticate, they will have keys, and somehow these keys may need to be updated, so you will have a key management issue on the board, on board. There is also some work about the time trigger Ethernet. I have a link there which points to the paper. There is less work on this for sure. It is also a bit more, or not a bit, it's quite more robust than the previous two. While on the space wire and space fiber, there is not much work and a lot of research is needed on this. This was just a summary of some of the challenges, of some research topics that could be interesting also for you, because I know that I refer to the academic community here. And now I would like to give you an overview of the technologies that ESA has identified together with the industry, with the European industry, as important to secure future space missions. We followed the logic of the typical cybersecurity frameworks. Again, we don't need to reinvent things, just to adopt and tailor where needed. Identify, protect, detect, respond, and recover. And over there, we saw what technologies are needed for each one of these topics. Each one of these bullets that you see there is a topic for R&D, for research and development. Maybe not necessarily academic research for some of them, but certainly a topic for development from industrial point of view. The bullets which have some kind of G nomenclature at the beginning, GT1Y, etc., are activities which have been published under a compendium called GSTP Compendium, was published by ESA 2 or 3 weeks ago, which is the basic, I would say, cybersecurity set of technologies that ESA invites industry for development for the next 3 years to come. If you go, I will not go through this list one by one, but if you have a quick glance, you will see that there are technologies for protecting the link, not only with crypto, but only about the RF part, like Transec, for instance, or some form of RF firewalls, of mitigations for RF interference, some quantum-resistant crypto. Just to make clear, it doesn't mean that this is something brand new. On several of these topics, there is already a lot of work done. This is just evolution of the existing, I would say, products, in order also to reach a higher TRL level, as we say. There are technologies about data segregation. You recall how many times I referred before on the need to have protection inside the spacecraft from different users. This is why data segregation is important now also on spacecrafts. This, of course, affects hypervisors, affects the avionics buses, affects network protocols, affects the switches/routers. Security monitoring, collect the logs, IDSs, transfer the logs. We're not talking about the same IDS. You cannot take an IDS and put it on the spacecraft for many reasons. First, it is too demanding as a processing power. Secondly, we don't talk about the same protocols, as you may have seen. But we need something, I would say, similar. And then, of course, to respond, how you respond when there is an incident, how you recover when there is an incident, how you bringing back your satellites in the previously secure state. So all in all, this is a pillar of technologies proposed by the agency for development by the industry in the years to come, or for further development. And these are some lists for topics for research for you, for the academia. It is not an exhaustive list. It is a list of topics that we believe it is relevant. It more or less touches the topics that I mentioned before, so I'm not going to mention them again one by one. Maybe something that I didn't mention explicitly is about, for instance, the routing. When you have this mega constellation thing, okay, you can have the routing in a kind of a centralized way, meaning that you know upfront what the route should be depending on the destination, but this is not necessarily robust because it may require some kind of reaction time in order to address, for instance, some denial of service attack. So you need some more flexible techniques. You can use, for instance, software-defined networking in order to adjust your routes, etc. Or security assessment of hypervisors or space operating systems, etc. I have heard that university also have CTF players, right? And we also like conferences, and this is why you are here and on this great conference. But ESA is organizing also a specific conference for space. Actually, it's next month in November, beginning of November at ESTEC in the Netherlands. This is the second edition of the conference. The first one took place in May of 24, again at ESTEC. The unique thing about this event is that we are going to have the first European capture the flag with 2 real satellites in space. In the first edition, in 2024, we also had the CTF, but it was based on a flat sat that we had on the ground. There were some teams, about 20 teams from all over Europe that competed at that time, and the top 4 came in ESTEC for the finals competition. You can see at the bottom left the picture of the awards of the winners. This year, the event of CTF was most successful because in the qualifications, we had about 560 teams that registered. So it was really very appealing to the community, and of course, we were very happy about it. And about 300 teams solved at least one of the challenges. And we will host the top 5 finalists at ESTEC during the conference for the final competition in space. Now, I would like to close my talk with giving you some heads up about what are the opportunities at ESA, especially for students. Because ESA has many programs that I believe are very interesting, and I'm sure that not many of you know about it, so I would like to give you some kind of a heads up. ESA has some internship programs which refer to or are meant to address master students or students who are still on the master degree, but close to the graduation. So they can, before the graduation, they can do, for instance, their master thesis together with us. But there are also opportunities for higher level, I would say, students, like, for instance, PhD students. There is a website, you can see it at the bottom right, ideas.esa.int, when you can find there that there are several options. There is options for co-sponsored research. If there is a topic that it is relevant for us, for ESA, you can propose it. This can be discussed. It will be discussed internally, evaluated by experts. And if it is relevant, you can be sponsored by up to some extent. I believe it is 50% of the cost, or up to 90K from ESA. Of course, it needs to address a research question. There can be system studies. For instance, you bring a new system study for a topic which is relevant for ESA. Of course, all this applies not only to security, but in general. Or to have some technology development activity, but the last one, I believe, refers mainly to industry, the last choice. There are also opportunities for visiting researchers, so it's not only about students. So if you believe that there are some labs that you would like to use, then this can become possible. We have many visiting researchers in different topics. Again, you can find this information to the links I provided. And my very, very final slide is just summarize what are the various entry programs for students at ESA level. I mentioned already the internship program. There is also the young graduate trainee program, which the name is changing, but principally it's remained the same, which this refers to students who have acquired their master degree and they want to do their first steps in the professional world. So they are hired by ESA for 1 or 2 years to work on some specific topics without any kind of, I would say, professional stress, but rather with some liberty in order to develop themselves and then to go back to the industry if they want, or to stay with ESA if there is the willingness and the chance. There is also the capability for national trainee programs, where in this case some member states can say that I want to send to you students in these topics for internship. In this case, these are paid by the specific member state directly. In my section, for instance, I had the interns, of course, I had YGTs, but I also had a national trainee from a couple of countries in the past. Postdoc programs, these are specific calls for postdocs. There were postdocs calls for cybersecurity or for 5G security as well. And the co-funded research that I mentioned before in the previous slide. So with this one, I would like to thank you for your attention. And if you have any questions, I'm happy to answer them. Thank you.
Thank you so much, Antonis, Atlasis, for your keynote and for your deep dive into securing outer space missions. And I think there probably will be some questions left. And I hope you will be there at the break.
I will be here, yes, so please feel free to approach me. Yeah.
Yeah, so just come to him and ask your questions, and he will be there to answer them.
Absolutely.
Thank you very much, Antonis, Atlasis.
Thank you.